In this video, we're going to look at the idea about isomorphic rings having the same structure. And we're going to actually start with a specific example. So I'm actually going to look at the following rings. So let's consider the rings Z6 and Z2 crossed with Z3. Now, both of these rings have 6 elements in them, and the question is Z6 isomorphic to Z2 cross Z3? Do these rings actually have the same structure? Are they the same ring up to the names that we give the elements? Well, this is kind of a hard question, so I'm actually going to build a potential isomorphism from scratch by explicitly defining the function on the elements of this particular ring. So what I'm going to do is I'm going to say let's let phi go from Z6 to Z2 cross Z3 be given by the following sorts of things. First of all, phi is going to send the 0 in Z6 to the 0 in Z2 cross Z3. And we already know that any ring homomorphism is going to have to send the 0 to the 0, so we'd better have that, otherwise there's no way this can be an isomorphism. I'm also going to send phi of 1 to 1, 1. And I'm going to make phi of 2 equal to, let's make it 0, 2. And phi of 3 is going to be defined to be 1, 0. And phi of 4 is going to be defined to be 0, 1. And finally, phi of 5 is going to be defined to be 1, 2. Now, if I start looking at this, it's pretty clear that phi is clearly onto the ring Z2 cross Z3 because we have every single ordered pair whose first coordinate comes from Z2 and whose second coordinate comes from Z3 accounted for. There's 0, 0, there's 0, 1, there's 0, 2. And here's 1, 0, and 1, 1, and 1, 2. So clearly phi is 1 to 1. Clearly phi is onto. And it's also quite clear that phi is 1 to 1 as well, because if I look at these answers, there are no duplicates. In other words, none of the elements in this set are being mapped to by more than one of the elements inside Z6. So phi is clearly both onto and 1 to 1, and hence phi might be an isomorphism. The real question is, does phi preserve addition and multiplication? Well, that's what we need to investigate, and there are several ways of investigating it, but I'm going to invite you to do some brute force. So what we're going to do next is we're going to look at these two tables. They are addition tables, and you will notice that they are currently blank. I want you to stop the video and copy these tables down and fill them out. Hopefully you stopped the tables and filled them out, and this is what you should get. I want to encourage you to again stop the video and check your answers before going on, because in order to understand what I'm going to say, you really have to verify that your answers are the same as mine. So hopefully you have done that. Now to check out whether or not phi preserves addition, I'm going to be looking at patterns, and I'm basically going to be using colors to keep track of things. So we're going to basically color every zero with this pretty green color in this table over here. And you'll notice that the zeros form a very distinctive pattern. Now what I'm going to do is I'm going to pick up the zero over here, because if you remember, phi of 0 was equal to 0, 0. So I'm going to color all of the zeros in this table that same nice pretty green color. And you'll notice that they fall in exactly the same pattern. And we're going to repeat this thing with every other element in our set. So we are going to go back and think about what phi of 1 was. Phi of 1 was defined to be 1, 1. So let's pick a color for phi. Let's pick a color for the ones. Well, let's make the ones this yellow color. In Z6, the ones are in these blocks. And over here, 1, 1 is there, and 1, 1 is there. Oh, I missed a green. So let's go back and color that 0 green. So now we're back onto the ones. So 1, 1 is there, 1, 1 is here, there's a 1, 1 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 here. And you'll notice that the yellow 1, 1s follow in exactly the same places that the yellow 1s fall over here. Well, continuing this, let's see, phi of 2 was defined to be 0, 2. So let's select a color for that. Let's see, we haven't chosen this color yet. So here are the 2's in this blue color. And I've now colored all the 2's in the Z6 table, this blue. And we're going to color the phi of 2, the 0, 2's, the same color over here. And when we do, you'll notice that again, they have exactly the same pattern. And let's see, the next thing that I want to consider is phi of 3, and phi of 3 was defined to be 1, 0. And let's see, let's use this pretty purple color over here, and we'll do a pretty purple color for the 3's. The 3's are in these spots over here. And let's see, the 1, 0's are there, 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 and there. There's 2 more 3's right there. And there are 2 more of these guys over here. So those 3's are all in the same place. Well, let's see, continuing on, we have phi of 4 is equal to 0, 1, and so I want to color the 4's in the Z6 table and the 0, 1's in the Z2 cross Z3 table the same color. And let's see, we will choose a light gray to do these. So let's see, the 4 is that light gray, and here are the 4's in that table, the Z6 table. And phi of 4, remember, is 0, 1. So we are going to color the 0, 1's exactly the same color in this table. And then finally, we have phi of 5 is equal to 1, 2. And we will leave the phi of 5's uncolored, and you'll notice that they also have the same pattern in both tables. So because the tables have the same exact pattern, so because our tables have exactly the same patterns, that tells me that phi does preserve addition? So now the question becomes, does phi preserve multiplication? Well, we handle that question in very much the same way. Here are two empty multiplication tables, one for Z6 and one for Z2 cross Z3. So please stop the video again. And once you've stopped the video, fill these two tables in. And once you've done that, then start the video back up. So hopefully you filled those tables in. This is what I got when I filled the tables in. I would encourage you to stop the video and check your answers before going on. Because again, in order to understand the patterns that we're going to find, you need to have the same answers that I do. So we're going to do exactly the same thing. So hopefully you did that. And now what we're going to do is we're going to do exactly the same thing that we did with the addition tables. We're going to start off with 0, and I'm going to color all of the zeros in this table the same green that I colored them in the last time, because what I want to remind you is that phi of 0 is 0, 0. And so we're going to color the 0 zeros in this table in exactly the same green color that we had previously. And you'll notice that that is exactly the same pattern. Now what I want to do is again remind you that phi of 1 was defined to be 1, 1. And when I did that, we picked a pretty yellow color for the ones in the addition table, so I'll pick the same yellow color here. The only ones that I'm picking up inside the table are these, and I find that I also need to go back and color some greens. So we'll do that in just a minute. So here are the 1, 1s. Now let's go back and color all those greens. There's a 0, there's a 0, there's a 0, there's a 0. Now I've actually got all the zeros in the C6 table colored. And let's look for the 0 zeros over here. There's 1, there's 1, there's 1, there's 1. And you'll notice that those new zeros that I forgot just a minute ago are actually still in the same place. And the yellow ones are in the same place. Well, let's see. Phi of 2 is supposed to be 0, 2. So let's color the 2's in the Z6 table and the 0, 2's in the Z2 cross Z3 table the same color. And we'll make them this pretty blue color. So here's a 2, 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 and there's a 2. And those are all the 2's that I see in this table. So now I'm looking for 0, 2's ordered pairs over here. And the 0, 2 ordered pairs are in these locations. And you'll notice that we have the same number and that they have basically the same pattern. Let's see. Phi of 3 is supposed to be 1, 0. And so I want to color the 3's in this table the same color as the 1 zeros in this table. So let's see. We're going to pick this light green, this purple color again. So there's a 3, there's a 3, there's a 3. On this row there are lots of 3's, and then down here there's one more 3. Well, let's see, 1, 0 is there, and 1, 0 is there. We pick up a 1, 0 there, we pick up a 1, 0 here, here, and here, and we pick up a 1, 0 there. And you'll notice that those purple dots all basically have the same shape and same locations. Well, let's see. We also know that phi of 4 is supposed to be 0, 1. So if I color the 4s in this table the same as the 0, 1s in this table, we're looking for the same places and the same colors. And I'm going to choose the same gray color that I chose last time. So in this table, there's a 4, there's a 4, here's a 4, here's a 4, here's a 4, here's a 4, there's a 4, and of course there's a 4. And over here I'm looking for the 1, 0 ordered pairs. And so when I'm looking for the 1, not the 1, 0 ordered pairs, I'm looking for the phi of 4 is 0, 1s. So I am looking for the 0, 1 ordered pairs to color in this light gray. So there's a 0, 1, 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 and here's a 0, 1. And just like before, we're going to leave phi of 5 which is 1, 2, uncolored. In other words, it will be in a white background. So the 5s over in this table have the same pattern as the 1, 2s over in this table. And now what I want you to do is stop the video and stare at these two tables for a few minutes. Now hopefully you did that, because what I want you to notice is that the colors on the two tables, the locations of the Z6 elements and the corresponding Z2 cross Z3 elements are in the same places. What I mean by that is that the zeros form this cross in both tables, but they also have these 4 elements in a circle. So they wind up being exactly the same in both tables. The blue 2s are in the same places in both tables. And the purple dots are in the same places. And the yellow dots are in the same places. There aren't that many yellow dots, so they're kind of easy to spot. The gray blobs are in the same places. And finally, the uncolored white things are in the same places. The 5s in the C6 table are in the same places as the 1, 2s are in the Z2 cross Z3 table. And so what we have from this table is that phi does preserve multiplication. And so what that says is that Z6 and Z2 cross Z3 really do have the same structure. It's just that we've named the elements differently. And so if we go back to where we originally defined the homomorphism, which I'm just going to write down one more time. So let's go to another page. We have Z6 over here, and phi taking Z6 into Z2 cross Z3, and 0 is sent to 0, 0, and 1 is sent to 1, 1, and 2 is sent to, 0, 2, and 3 is sent to 1, 0, 4 got sent to 0, 1, and 5 got sent to 1, 2. You'll notice that basically the names of the elements changed, but in these two elements on each row are interchangeable depending upon what we want, depending upon what ring we are actually in. So in Z6, Our elements are these guys, and in Z2 cross Z3, the elements are these ordered pairs, but because the tables look the same, the two rings are actually indistinguishable from each other except for the names of the elements. And that's true of any pair of isomorphic rings. The only difference in their structure is what do you actually call the elements. But if you looked at the actual structure, the multiplication and addition tables, and order the elements according to the the isomorphism, the two rings will have exactly the same structure. And so to just tie this up, we know that Z6 and Z2 cross Z3 are exactly the same ring up to isomorphism.